So this video is documenting the new and upcoming release of gpvdm. The major new feature in this version is the ability to do ray tracing, so effectively look at how light escapes from sort of 3D structures and exits the device. Now the ability to do ray tracing has been in gpvdm for a while, but it's only been in 2D and not 3D, and also it's never really sort of been expanded as a feature, as sort of, you've not been able to get as much information you'd like to get out of the simulations, but hopefully this release will change that. So if you go down to the new simulation window that you can get from here, there's now a new demo simulation called Ray Tracing Demo. So if you double click on that and save it, say on the desktop, and we'll call it a file called Ray Demo, so that's what we're going to save it as. We get a device structure like this, and this device is just to effectively demonstrate the ray tracing demo, and it's comprised of two layers. So there's an aluminium layer here, so some metal, and there's some arbitrary organic layer here. So if we look at the layer editor, they're both about 400 nanometers thick. Now, before we look at ray tracing and how light escapes from the device, first we need to know what the optical profile of the light that's being generated in our device is. Now, previously, you've been able to calculate that by using sort of the PL simulation, but very often you don't want to simulate how the exact profile of the PL. You'd rather just use a given value from an experiment. So if you look in the database tab, there's now an emissions database, and in this emissions database, I've populated it with some various spectra from various organic materials. So this is effectively how you'd expect light to be emitted as a function of wavelengths from these materials. So here's some four materials, so let's just pick one here, and this is how you'd expect it to be emitted, and then if you pick another one here, that's how light would be expected to be emitted from this material as a function of wavelength and intensity. And you can add more spectra to that if you want at will. So what the simulation is going to do is take that optical profile and effectively propagate it out of the device and sort of see how much light escapes. So if we run the simulation, what it's going to do is take a point right in the centre of the device, so right in there, and see how all the light escapes. So let's just run that simulation and let it go. So it's going to run this as a function of wavelength. And up here on the right hand side it says mag, and that's mag, we'll just go back to that, that's the magnitude of the light in the input spectra. So you can see effectively it starts down here at 514 nanometers, and then it increases to a peak at about, I don't know, what's the peak? There we go, 563, and then decreases down there. So it's effectively a Gaussian. And then if we look at the output, whoops, there's device structure. This is what it's simulated. So it's effectively projected rays out of the device and looked at how effectively they propagate in the device over effectively this angle here and then this angle here. Now it's a bit hard to see what's going on because we've got this device in the way. So let's take off the device. So if we go show and then take device off, we can actually see the rays a lot better like this, and we can see what's going on a bit better. It's actually still, so there we can see there's our point source in the centre of the device, and we've got all this light propagating outwards. So it's still a bit hard to see what's really going on there. So what we're going to do is take down the number of rays that we've got in our simulation. So if we go to simulation editor, then ray tracing editor, and instead of having 200 steps around theta, which is the vertical direction, we'll change that down to say 20, and then if we run that again, we'll get less rays so we can see what's going on. And what you can effectively see is the rays being propagated out of the device, and you can see this sort of zigzag pattern because effectively you're getting internal refraction. So light's going zigzag up there and down, and it's effectively bumping off and down the layers. You can look at the so you're used to looking at a device like this through the device view, but it sort of blocks what's going on. It's quite hard to see. So what you can do is if you turn that off and you look at the ray tracing mesh. So this is the mesh that the actual ray tracer uses, and it shows you sort of the outline. And you notice that everything in here is made up of triangles. So this big box is effectively your simulation world. So this is where the simulation ends. It's made up of big triangles. There's a triangle. Where's the other triangle? There's another triangle, etc. And then if we zoom in, this box here is the organic compound, this box here is the aluminium compound or material, and you can see effectively how the rays are bouncing about inside your organic material and how they eventually escape. So let's go back to the simulation editors and bump up the number of theta steps to say 200 again, and we'll just run that. It takes a bit longer, obviously, because we're propagating more rays. And there we are. And we'll just get rid of that ray tracing mesh, and we'll pop back on the device. Now, that's all very interesting. And what we can now do is we can run down this as a function of wavelength, and effectively see how the angle of the light emitted from the device changes as you go through various wavelengths. Now, what's very interesting, if you want to sort of design OLEDs and things like that, is to see effectively how as you look at this device, a function of angle. So as you look at it like that, or like that, how the colour effectively changes. And this is interesting for things like designing television displays, because you want sort of wide angle, or the colour to be effective from your OLED to be the same from a variety of angles. So if you go to the output button, you can see there's, what's the first thing? So the first thing we can look at is angle escape.dat. So what this is angle, so this angle, so that's 0, and that's 180 degrees. So if we look at it here, 0 degrees is effectively there, that's 90, and that's 180. Let's check we're still recording, we are. And this effectively shows you the intensity of the light as a function of angle here, and this is wavelength. So you can look sort of how angle and wavelengths change as you look at the device. The other thing we can look at is the colour as a function of angle. So what I've done is I've taken the C, I think that's called the CIE International something. It's a spectrum effectively that defines how your eyes see colour, and I've calculated from this here the RGB values that your eye would see. So this is effectively the colour you'd see in terms of RGB. And so this is, if you're looking at it from 0 degrees, you'd see nothing. Then as you got towards sort of, I don't know, 70 odd degrees, you'd start to see some green, then some orange, and more orange, and eventually go back to green. So you can see how your eye would see that. And on the top right, you can actually see the up there. You can see the RGB colours there that you'd expect to see. The other thing is the input spectrum. So this is the input spectrum. I can't remember which material this was we used, but the colour of this line is actually the colour of the input. So you can see effectively how the structure, by comparing this graph, or the colour of this graph, and this, you can see how effectively the structure's changed the colour of the light your eye would perceive due to the viewing angle. So that's really it. There's going to be a lot more to come on this 3D ray tracing. I plan to do other things like add lenses and things like that. They're all actually relatively simple to do now. I've written the main ray tracing code. The final thing to probably point out is that this ray tracer now has got its own simulation mode, just like a JV curve, so you can just perform ray tracing simulations at will. You don't have to run OLED simulations or anything like that. You can just do a ray tracing on your structure. So yes, I think that's it. I hope you enjoyed this video, and I hope you find this feature useful. Thank you very much.